Cool. Thanks, Cam. And thanks you guys for being here. It's a really exciting event, and we're really happy to host it in Edmonton this year. So I'm going to talk to you about natural language processing, which is basically the field of study that tries to get computers to understand language. And I hope part of what I'll impress upon you today is that is actually a really hard task. And it's nowhere near solved, despite what you may have heard. Before I do that, though, I always tell everybody how to say my name in case I ever meet you in the future, or maybe at coffee break. My name is Alona Fyshe. So Alona is my first name, and Fyshe is my last name. So that's how you say it. I'm originally from Edmonton, so this is actually my hometown. After I did my undergrad and my master's here in Edmonton, I moved to Pittsburgh. Originally, I moved to Pittsburgh to work for Google. But after a couple years, I decided I wanted to get back into research, so I quit Google and went to do my PhD at Carnegie Mellon. After that, I moved to the West Coast and was a professor at the University of Victoria for 3 years. And I actually just moved back to Edmonton last summer, so I've been here for 1 year. I love Edmonton. I hope you guys are enjoying it too. You've gotten pretty much the whole range of weather that Edmonton experiences in the summer. So we packed it all into a very short period of time just for you guys. And it's beautiful and sunny today, so I hope you get a chance to go outside. So what I actually study, I probably won't get a chance to talk about today. My main sort of field of study is studying how the brain represents language, and in particular language meaning. So how are you understanding what I'm saying right now? What is your brain doing to represent these concepts? How are you putting words together? And what does the brain look like when it's doing that job? And something that's been really interesting recently is that the brain actually looks a lot like neural networks. So it looks like a convolutional neural net when it looks at pictures, and it looks a lot like an RNN when it looks at language. So those are two really neat recent findings, and those are the sorts of things that inspire my research. Because if we could understand how neural nets worked, it might also help us to understand how the brain works. Anyway, but today we're going to talk about natural language processing, which is like a huge field. We could spend an entire semester on it and still not cover everything. So it's a gigantic field. We're not going to talk about everything today. Today we're going to just talk about the meaning of single words. So it's a very simple concept. It's easy for you to understand. One word has a particular meaning, and we're going to talk about the ways in which we can test our modeling of that meaning. And then at the end, I'll talk about one piece of my research in which we compared the computer models of word meaning to convolutional neural nets, and the kinds of meaning that convolutional neural nets learn. So NLP is incredibly interdisciplinary, so you guys would fall somewhere on the statistics and AI curve. My training is mostly in statistics and machine learning, but I do have a bit of a background in cognitive science, and I learned some linguistics just by doing computational linguistics. So if there's a linguist in the audience, you probably wouldn't consider me a linguist. I don't consider myself a linguist either, but I have a little bit of linguistic knowledge. So it takes some subset of all of these in order to really push this field forward, which is part of the reason I find it fascinating. And I think it's part of the reason that it attracts a very diverse audience. So it attracts people who speak many languages. It attracts women as well as men. So the conferences can be really fun places to be. The main question behind natural language processing is, can we get computers to understand language? So do you think computers currently can understand you? So raise your hand if you think the answer is yes. One devil's advocate in the room. Okay, got my eye on you. So you're probably all aware of Siri, the Apple's personal assistant, personal digital assistant. And you may have interacted with her on some scale. You may have asked her to do something for you. There's a lot of things she can do very well. So for example, she can place a phone call for you pretty well, put a date on your calendar, start an alarm, set a timer, so on and so forth. Those are the things that Siri does really well. But if you ask Siri to do something outside of that realm of things that she's used to, she often falls short. So here's an example where somebody said, "Quick, call me an ambulance," and Siri said, "From now on, I'll call you an ambulance." And can you imagine if you were that person? You were like, "Thanks, Siri." And so this is actually kind of an old example. They've since fixed this, you'll be happy to know, so you can actually ask Siri to call you an ambulance. But I more recently, every time I do this presentation, I give Siri another go. So not too long ago, I did this. I said, please place a call to like a particular number. And I said the number, like 780-987, da-da-da-da-da. And Siri said, I can't find anyone in your contacts named 780. Like, so the real world knowledge required to do this task is huge, right? You need to understand that people's names are not numbers, right? Yeah, and that nobody would be called 780-978, whatever. That I'm asking you to, and phone numbers are numbers, so I'm asking you to actually dial those numbers into the phone for me, please, Siri. So Siri's still sort of stuck in this state where she does a lot of things really well, and I bet most of the time she does a great job, and then there's that sort of edge case where you're just like disappointed. And if you have some of the new at-home devices like Alexa or Google Home, maybe you have these experiences more often. Especially, I have a young daughter, she's 4, and she often asks really interesting questions, and so we'll ask Alexa, and Alexa is just like, I don't know what you're talking about. She often wants to, yeah, she asks questions about popular TV shows. Anyway, so this is the problem of the long tail, and this is something people in natural language deal with a lot. So 80% of what you want to do with Siri is easy. Actually, you could build a rule-based system and get pretty far. Most of what you want to do with Siri is you want to set your alarm and your timers, and you call somebody who's, you're going to say their name, not a phone number, and you want to, put something on your calendar, so on and so forth. Those are easy to do. But the remaining 20% are incredibly hard, and they just get harder. And so in order to cover this full 100% of the span of things you might want to do with Siri is really difficult, and you would have to essentially solve AI to do it. You'd have to build an agent that could handle anything a person could. So I think I already asked you this. Can computers understand language? I think we can say to a certain extent they do. They've certainly got a lot better, and speech recognition in particular has gotten a lot better. But what would it take to convince you that a computer could understand language? Aside from the Siri task, is there something that you would like a computer to do, and if it could, you would be satisfied? Paraphrase. Paraphrase is a great one, and that's something that actually computational linguists love to try to do paraphrasing. And a lot of the approaches to paraphrasing are essentially taking words from the document, like deleting words and using words from the document and putting them together to make sentences. So it's actually like a little disappointing when you find out that that's how they do it. But there are some more complex and rigorous examples more recently. Anybody else? Make a good joke. That's a good one. So Siri tells great jokes. She does, but they're from a dictionary of jokes, of course, right? So maybe a back and forth banter, and that's something Amazon has had a competition going for a while to have a chat bot. So you could try to talk to your Alexa app and see how good she is at sort of holding a conversation. So maybe that's something we could add to it. So not just tell a joke, but sort of have a humorous conversation, something that would require like understanding the world and what people would find funny. Anything else? Sarcasm. Sarcasm's a good one, yeah. Invoke questions from the context? Oh, invoke questions, so ask questions. That's an interesting one. So there's a lot of question answering in natural language processing. We like to have data sets, like give you a paragraph and a sentence, and you have to answer the question, but it's an interesting task to make up the questions instead. James? Recover from errors, so that's a great one. So Siri and Alexa right now, when they make a mistake, they just say like, sorry about that. Like it's not, but it would be interesting if they could say, wow, I don't know what you mean. Are you looking for like this kind of information? And then like actually an iterative process would be really cool. Okay, one more. Yes, exactly. They don't follow the context. So they not only do they kind of get when they can fail, but they're not very good at figuring out why. Good. Okay, so we are a long way off from a lot of what you talked about, but I think you have an idea now about how hard it would be to build a system that could do that thing. But maybe before this, you had sort of not thought about how hard it is to do language. Language is actually a really complicated system. It's full of culture. It's full of ephemera, things that are just now and not in the future and not in the past. We make up words all the time. We talk about things that don't exist in the real world, and it's a very complex and ever-changing thing. So if you could build an agent that worked perfectly right now, it probably wouldn't work in 20 years. And language is full of ambiguity. So here's some interesting examples. Juvenile court to try shooting defendant. So as in they are going to attempt to shoot the defendant is actually not what they're going to do. Rather, they're going to have a trial. Hospitals are sued by 7-foot doctors. So the doctors are probably not 7 feet tall, right? There's probably 7 of them. And then there's the more like patents. Alice saw Bob with a telescope. So does Bob have a telescope or does Alice have the telescope and she's looking through it? It's unclear. I'm going to skip this example for now. So language is complex. I think we see that now. So let's start simple. Let's start with just single words. So that's what we'll talk about today. We could actually go simpler than single words. We could actually go below the word level. And some of the models that you've heard about RNNs, right? Joshua talked about RNNs. Yeah. Do you talk about character level RNNs or just word level? So you can actually build RNN models to predict not the next word, but rather the next character in the stream of characters. So we consider the string to be not just words, but actual characters. So we could do that, but not today. So, and there's also the idea of a morpheme as a word part, like in running, ing and run are both morphemes. So we could also build a model that understood that breakup of word parts. But we're not going to do any of that today. Instead, we're just going to talk about the word level models. And that's partially because it's more intuitive. So working at the word level makes a little bit more sense because in English we have these spaces that demarcate words. And so it's easy for you and I to think about how we would build a lot of these models. So what we want to do is represent the meaning of words. Somehow we're going to build a model that has, for each word, some representation of meaning. So let's start by thinking about what it means to mean something. And the way I'm going to get you to do that is I want you to tell me something that's like an orange. You're really good at this, just yell one out. What? Ball? Oh, that's a good one. I've never heard that before. Any other? Apple's a good one. Clementine's a good one, very nice. Anybody else? There are no wrong answers. Ball is not a wrong answer. Although it would be interesting to ask how many of you were thinking ball, right? And actually that's part of what we're talking about today. So anyway, apple is one I often hear. Banana is one I often hear. So these are fruits, right? I don't hear car, never heard car. I've never heard sandwich. Even though a sandwich is something you eat, right? So what is it about sandwiches and cars that makes them different from fruit? And so we can think of if we had a semantic space, we had a representation of meaning in our brain that only had 2 dimensions. We only understood whether or not something was sweet, and we only understood whether or not something grew on a tree. We'd find our fruit in the upper right-hand corner, and we'd find our car and sandwich in the bottom left-hand corner. And maybe cars. Yeah, where would lemon be? So lemon is an atypical fruit in that it's not sweet, so he'd live over here. And maybe sandwiches are slightly sweeter than cars. I've never tried a car, but could be. So anyway, we end up with this representation, and this representation tells us that fruit, these words have something in common, and these words have something else in common, or at least that these words are different from these words. So this is a really simple vector space model of semantics, or a word embedding model. And it's called a vector space model of semantics because each one of the words in this very small data set has associated with it a vector of numbers, and that vector of numbers just defines a point in space. And words that are similar will have similar vectors of numbers. So all of these words up here, apple, banana, orange, have very similar numbers in their vector. So here are the number vectors, and they look very similar. But if we want to be able to differentiate not just between this simple set of 5 things, we're going to need really big vectors, or else all of our points will be really close together. We won't be able to tell them apart. So what we do is we take our vectors, rather than having 2 dimensions, they have hundreds of dimensions. So we're going to build these big vectors such that words that are similar are going to have similar vector numbers. They're going to appear in similar points in space. So if you think about similar words, so here are some synonyms for the word beautiful, so pretty, lovely, handsome, attractive. If you think of synonyms for the word big, enormous, huge, immense, gigantic, what it means to be synonymous means if I had a sentence that had this particular word in it, I could take one of these other words and substitute it in. And so that means that context tells us something about word meaning. So if 2 words have very similar meaning, they're probably context, you could swap them in and out of context, and the sentence would still make sense. And from context, you can infer meaning, is really the main point of today's lecture. So here are 4 sentences. Can you guess what tesquino is? It's a drink, yep. Is it a special kind of drink? It's probably alcohol, yep, if it makes you drunk. So you are using context to infer meaning. So you probably do this like if you're reading a book and you're too lazy to get out a dictionary. Sometimes you like hit that word and you don't know what it means. But if you keep going, like pretty much you can figure out what it meant, right? Some of the time. So we're really good at this, and it turns out that computers are going to use that same notion, that we can figure out what a word means if we look at the words around it. And if we have enough examples of that word in context, we'll be able to figure out we'll have a really good model of what that particular word means. So what we're going to do is build a vector for each word, and the way we're going to build it is by training on the context around words. So we're going to train on the words we see together. And together can be defined in a lot of ways. It can be defined as being in the same document, so on the same web page, for example, in the same sentence, or within a few words of the word we're interested in. So the model we'll talk about today is called skipgram. It's a neural network. It works like this. So we have a central word. So for example, here our central word is banana, and there's some context around it. I want to build a model that can predict these context words if I tell it the middle word. And the way we're going to do this is using a large text corpus scraped from the internet, and we're going to parse it in order to make these word pairs. So I'm going to make a pair of words that I saw close together and then train my model so that it can, with high probability, predict those probable context words. So the skipgram model is actually really simple, just one hidden layer. The input is a one-hot vector, so that means that for each word, this vector has only one on bit at a time, only one on node. And it corresponds to the context word. So for the word banana, for example, it would be this one particular node on. And we train it so that the output is a probability distribution over all words, and we would like this probability distribution to have a high value for words that are probably near the word we're interested in. So this is how we're going to train this model. So we want it to give us high values for words we often see with the context word. And a byproduct of training this model is that we end up with this hidden representation in the middle layer, and that hidden representation is going to become our word vector. So it gives us a sense of what the word means. And our hope is that words that have similar meaning have similar context, and thus they'll have similar hidden representations in this middle layer. So a little bit of math. So if we have, let's say this is a sentence, and I'm interested in this word in the middle, WT. So I have two words before and two words after. I'm going to learn a matrix W and C to perform this task of predicting probable context words. So we're going to say that the hidden representation size is of size D, and V is the size of the vocabulary, the number of input words. So what I want to do is learn my matrix W and C such that the dot product of a context word and the word of interest is high, and it's low for words that I don't see in context. So I would want like eat and banana to be high, and banana and ice cube, igloo maybe, igloo to be low. So what I'm going to do is parse my corpus to make some word pairs here. So here W is my central word, and I have 4 context words, tablespoon of preserves or. I want the dot product of the vectors for these 2 words and these 2 words with this middle word to be high. And then I'm going to choose some random words that I didn't see in this sentence, in this nearby window. And I want the dot product of W with those vectors to be low. That's essentially the whole point behind this algorithm. So I want the words I do see to be probable and the words I didn't see to be less probable. So if you write that into math, it looks something like this. So here are the 2 words we did see together. We saw the word C, the word that has vector C, and the word that has vector V together. And here I am sampling a bunch of words from the probability distribution over all words, such that, and I'm taking the dot product of those things. So I want this value to be small and this value to be high. Now, this is kind of like a funny idea to just randomly choose examples that you think you probably wouldn't have seen. You choose them randomly, so the chances are you wouldn't have seen them with the word banana. And the reason we do that is actually from the formulation of this conditional probability. So this conditional probability has the form that the thing we are interested in modeling is in the numerator, and the denominator is the sum over all of the other possibilities. It turns out that this can be expensive to calculate. So this formula here can be expensive to calculate. Does anybody know why? Right, V is gigantic. V is like 10,000, right? 30,000. V is a very large set of things. And so to do this sum, this is just for one value. To do this sum is very expensive. And so instead we approximate it by just choosing random words. So we approximate this denominator by choosing random words. So this is called negative sampling. So we're sampling from the negative training set you can think of. And we select maybe 10 examples. And the idea is that in the limit, this looks essentially like what we're trying to model. Okay, so after we do this training process, we end up with this very small neural network that gives us word representations as the hidden layer as our word vectors. And so we can train these word vectors and do some interesting things with them. So we'll talk about that now. What could we do with these word vectors? So one thing we can do is watch word meaning change as a function of time. So if we train our model with just data, example here from the 1900s, around 1950, 1975, 1990, and 2005, if we train on little windows of data, we can see how word meaning changes as a function of time. So gay used to have a very different meaning a long time ago, and its meaning has changed as a function of time. And the same is true of broadcast. Broadcast is an interesting word. You all know what broadcast means now, like the radio, right? So what did broadcast, does anybody know what broadcast used to mean? Seeds, yes, exactly. Isn't that interesting? So it came from a word for spreading seeds. So you would broadcast the seeds, which is what you do with signals too, right? So it's a metaphor. Anyway, so we would see a similar pattern for broadcast. The meaning of broadcast also changed as a function of time. So because of these context effects, how people use language, we can see how language is evolving. Okay, so we have word vectors. Let's say I train a word vector model and you train a word vector model. I want to be able to tell whether yours is better than mine. You have a question?
So I guess my question is, the meaning has changed, but it's the primary meaning. Like we still have that secondary meaning that exists for broadcast.
Right, it's not as popular anymore, which is why the sort of, when you train on the text that appears now, you will still get some of that meaning, but the more dominant meaning is the one that has to do with like signals.
So is that accounted for in the models?
Not in that model. It just shows the dominant meaning. Any other questions? Okay. Okay, so now we want to figure out if your model is better than my model, as we often do in machine learning, right? It's like what we like to do. So we need a way to figure out if my model is better. So we need a way to judge a model's fitness. And what we want to compare it against, of course, is the actual true model of language, which doesn't exist, right? There's no book we can look that up in. Each one of us carries around in our head our own version of what words mean. And actually, our personal version of what words mean might be a little different depending on our backgrounds. So there's no true answer for what we should compare against, so we're going to figure out some proxies. So essentially we have our distributional model here, and everybody is walking around with some sort of model in their brains that tells them something about what the word meaning looks like. So you have some model of word meaning, I have some model of word meaning. If we could measure the axes of representation in your brain, they would not have anything to do with the axes in our word model. But it's possible that the relationship between words in the word model is consistent. So what I'm trying to represent here is that these axes are sort of, if we swap this on its head, it might not look like these two spaces were the same, but the distances between nodes in these two spaces would be preserved. So the axes don't need to be shared, but if the distances between points is consistent, then we'll call the two models similar. So essentially what we want to do is measure the distance between words. So what we're going to do is we're going to calculate the distance between words in our vector space. And then we're going to ask people to calculate the distance between words in their vector spaces, in their heads. And then we're going to compare those two lists of numbers. So if my vector space gives a particular set of numbers and yours gives another set of numbers, your brain model gives a set of numbers, what we want is for those numbers to be correlated. So things that are close for me are close for you. So there's a little trick here. How do we get the distances out of people's brains. So if I had my other hat on, I would tell you we could just do brain imaging. And we'd actually just take pictures of your brains to figure out which words you think are similar. So that's one thing we could do. But another thing we could do is actually give people pairs of words and say, how similar is this pair of words? I want you to tell me from 1 to 5 how similar this pair of words are. So there's lots of data sets for this. One example is Simlex 999. And it just contains a bunch of pairs of words. And what they did was put on Mechanical Turk some questions about these words. So how similar do you think these words are? People rated them, and then they aggregated over a whole bunch of people who had answered the same questions. Mm-hmm. That's an excellent question, and that's actually one of the things that this particular data set tried to address. So it had been in the past that people just said, tell me if these words are similar, but similarity has like different aspects. So cars and wheels, you could say like are related. They're not the same, but they're related. And so people might give like higher scores to cars and wheels when that's not actually what we're interested in. We're interested in like car and vehicle or car and truck. We want those things to be similar. Yeah, that's great. So I'm not talking about the fact that one word can have multiple meanings at all right now. I probably won't at all today, but that's actually a problem with word vector models is that often we do not try to differentiate between word sense. We're just going to collapse them all down into one vector. And so oftentimes the most prominent word meaning will be the one that dominates a word vector. And what's also not, so I think you can kind of, from the context of the word pair, get the meaning that would give you the most similarity, but you're right that if people are just not primed for that word meaning, they might not answer consistently. Which is why we might want to ask many people. So if we have a word pair that nobody answers consistently, then maybe we want to throw out that word pair. Any other questions? Okay. So here's some examples of word pairs. So alligator and crocodile. So people gave that these are examples, but people gave it a 5. And if I calculate the correlation and then scale it between 1 and 5, maybe my vector space model gives that a 4.5. Cup and mug, 5 and 5, and then potato and shoe, like those are not very related. So people said 1, and the vector space model says 2. And so if we have these two sets of numbers, I can calculate the correlation of those people answers to my word vector distances, and you can calculate the correlation to your word vector distances, and we can get a measure of how good our two data sets are, our two models are. So that's one way of evaluating word vector models. Another way is to do these word analogy tasks. So I'm assuming some people here are from America? You're from America. Wow, that's phenomenal. How did we not get anybody from America? Everybody who's from America is shy. Oh, I see one American. Okay, so in America, they have this thing called the SATs, and they often include word analogy tasks. So you've probably, even if you're not American, you've probably seen questions like this. Hammer is to nail, a screwdriver is to screw. Very good, guys. So they give these tests to people who are in high school, and they ask them to answer them, and they do particularly, I don't know, let's say like 60%. And word vector models can do about the same. So word vector models are about as good as high school students on this task. So maybe you're impressed. If we can do as good as high school students, maybe you're not. Anyway, so I'll tell you how we do this. So here I have a set of 4 possible words that the screwdriver could, hammer to nail a screwdriver is to question could be answered with. And I'm going to have word vectors for all of them, as well as for hammer, nail, and screw. So I'm giving a set of words of A is to B as C is to D, where D is one of the example answers for my list. I'm going to find the vectors for all 4 of those words. So I'm going to look into my skip-gram model. I'm going to take that center hidden representation for each one of these 4 words. I'm going to use it to answer this question. And it turns out we can do it with math. So the thing I'm interested in computing, this vector y, I'm going to compute it by taking the B word and subtracting A and adding C. And so if I do that, I get some word vector y. It's an approximation of a word vector. And then I can sort all of the other word vectors in my model by the distance to that approximated y vector. And if the correct word vector is the closest one, then I say I get the question right. So essentially, the computer's doing something like what your brain is actually doing. It's choosing from the set of all possible words the word that it thinks is right. And people often exclude actually A, B, and C from this set. of words, which is a bit of a trick, but it's something you would do too, right? You would, given this question, A is to B is C is to question mark, you wouldn't answer A, B, or C to that question, right? Okay, so here's one benchmark data set created by Google. And so some of the questions in this data set are what we would call semantic. So common capital city, Athens is to Greece as Oslo is to, and then we would have a list of countries, and Norway would be one of them, and Norway would be the correct answer. City and state, Chicago is to Illinois as Stockton is to California, right? So on and so forth. And then some relationships having to do with gender and so on and so forth. So these are the semantic relationships, and they also have sort of linguistic relationships. So great is to greater as tough is to, I know you can just read off the slide, but you would say tougher, right? Switzerland is to Swiss as Cambodia is to Cambodian, so on and so forth. So these are sort of working at the word level, changing the word form in order to fit the pattern. And these are more world knowledge. You would have to have some world knowledge to answer these. And so this is the state of the art. So semantic is the top half of that table we just looked at, and syntactic is the bottom half. And so we can see that some people have done incredibly well on these tests, so as high as 80% on the semantic and a little bit lower on the syntactic, which is, I think, pretty amazing. It's possible to answer these questions that seem pretty abstract just with vector math. And so what does that mean? That means that the underlying representation, the vector space that is behind all of these words, actually has properties encoded in direction, right? That means that there's a direction in my space that is gender, that is what it means to be more or less woman. So if I move along this direction, I go from things that are male, like uncle, towards things that are female, like aunt. So the relationship between man and woman is encoded in a direction in this representational space, which you don't seem sufficiently blown away, but like that is amazing, that is a property of this word space. And the same thing here, so here's pluralness here. So king goes to kings and queen goes to queens. So the idea of changing to be plural is also a shift in this embedded space. And that's not a function of the algorithm. Now scriptgram, right, doesn't know anything about what words are plural, right? This is a one-hot vector. It doesn't even know which word is the plural of which other word. It has no concept of words at all, actually. It just knows which words it sees together. So from that information, which words it sees together, it's able to pull out this pattern, which is just remarkable if you ask me. And that should also make clear that it's not a function of the model, which means it's a function of the data. So this appears in the data, and if you run a reasonable enough model on it, you're going to get out these patterns. So although this particular this test was associated with a particular model, it's not the model that made this test possible. This test is possible on most things trained on corpus data. And corpus just means a large text collection. Okay, so we have these word vectors, and they can answer these analogy tasks. So we get man is to king as woman is to, was on the last slide, queen, very good. Here's another question for you. Man is to programmer as woman is to programmer, yes, exactly right, but guess what? The word vectors do not say that. They say homemaker, which shows you that data is not just data. And so you were at the panel, hopefully, on whatever day that was, Wednesday, where we talked about ethics in AI. So you are not immune to this. This is happening because the data you train on has bias in it, right? And so you have to consider that. What do you do if your data has bias? Your data does have bias. What are you going to do?
So in addition to the bias in the data, some paper pointed out that the trick that you mentioned, that like for the choices that you get, man, programmer, and woman are omitted from the choices that you get. How convinced are you by that? Like how convinced are you by that? Like saying that the model didn't have that choice of programmers.
It couldn't say programmer, but they could have said like developer,
okay,
or engineer, or homemakers. I think we can all agree that homemaker is pretty far from what it should have said, right?
Maybe engineer was like a little sick.
Yes, that would be lovely. And actually, so I had I taught a natural language processing class, and as I was doing this example, one of my students was like checking on using the corpus, the model that he had like built that day, and was like, it's not true in my data set. So it's not true in all data sets, and you know, you'll find differently offensive things in different data sets. Okay, so but my point is that if your data has bias, you better believe your model's going to have bias too. And it turns out that your models are not going to be just as biased as your data sets. They're going to be even more biased. So if you're, well, we'll talk about it, but if you have a little bit of gender bias in your data, your model is going to have a lot more gender bias. And that's the problem. So we could say if their model is only as bad as people are, as racist or sexist as people are, maybe that's okay. It's not, but maybe it is. But it's not what happens. The models actually are more racist and more sexist than we are. And that's a huge problem. We don't want to go down that like, right, that doesn't end up anywhere good. So here's a sort of an illustration of what this looks like. So on the y-axis here, we have the predicted gender ratio. So that's, you can interpret that as what the model is doing. So this is what the model is showing for a particular word. And here is the training gender ratio. So in the training data, we get this number, and when we test, we get this other number. That's sort of what you can think of. So for a particular example here, washing, in the training data, the ratio is about 0.3. Sorry, and I should say here, low numbers are female and high numbers are male. So here, washing is a 0.3 in the training data and a 0 in the predicted model, right? So that means that the shift in gender sort of disparity has gone really strongly to the female side. And so we can get that by just sort of looking at this graph and squinting our eyes and seeing how far these dots appear from the center line. So if there was no bias, if there's no difference between training and predicting, then everything would be exactly on the line, right? For every input number, we would get the same output number. Yeah?
Isn't it also true that we need to look at kind of like a time series analysis of this, because at different points I imagine that these numbers would.
Right, yeah. So the question is, wouldn't this change over time? And you're absolutely right. So maybe washing is becoming less gendered. That's totally possible. And certainly being an engineer is less gendered than it used to be. So we can imagine that if we built a model over time, we would hope that these things were sort of collapsing upon themselves. Or maybe, no, rather we would hope that these words some of the words were moving more towards center. So that's what it would actually be, would be that there's no bias in the words themselves. Anyway, so what we're looking for is, so these are two popular data sets, and what we would like to see is that all of these words lie right on the blue line, but it's not what we see. But this is an example of a correction that you could do. So this is the two original data sets here that I just showed in the last slide. And this is the correction they've done to try to get these points to fall within what they would call like the margin of error around that middle line. And so they're able to successfully push some of them back into that acceptable margin of error. So this is all just to say, without telling you any of the background, that there are methods for trying to reduce this bias that we see. It's an open area of research, but it's certainly something that's active and not solved by any stretch of the imagination. Yeah?
So in the previous example that you showed, so there are some words which are like gender neutral, like programmer, and like some words like kings and queens, they depend on the gender.
Mm-hmm.
So do you think that has also to do something with bias word difference?
So this is just saying that we would like our models to be as gendered as our training data. So if king is a male word, it should be both male in the training data, and it should be as male in the model we train on it, is all this is trying to say. So you're right, that words do have gender associated with them. Mm-hmm.
What makes the model be more gender biased more than its input data?
That's a great question. So that's something I didn't say. So why is a model more biased than the data? Does anybody have an idea?
You're reducing the dimensions, so it has less meaning now.
So right, like the idea behind it is when we do machine learning, what we're trying to do is leverage patterns to make predictions. So if we see a pattern, we're going to grab onto that and use it to as big as we can, as our greatest advantage, to try to do really well on our data. So we're going to take a pattern and we're going to use it as much as we can. And that means that sometimes we use it so much that we expand upon bias. We make bias bigger. So that's the problem here. So the question is, should we train in a different way that maybe gets us it might get us less accuracy, but it would be less biased.
So you said something that wasn't immediately clear to me. You said if we train our models over data sets with respect to time, then the sensitivity to these issues will get less.
Well, so the question is, did I say that if we train our models over time, meaning the data spans time, will our models become less biased? So no, only if the data becomes less biased, is what I'm saying. So if we are becoming a less biased society, then the data would become less biased and we would train better models. That's possible. Okay. So anyway, so the point here is just we're trying to push these dots back to the middle line, and you can see that at least for some of the words, that's possible. Now the last thing I want to talk about is convolutional neural nets and word embeddings. So you talked about convolutional neural nets. Yes, some nods, that's great. They are models, as you know, trained to, from an image, predict what's in the image. So here's a very simple picture of something that kind of looks like a convolutional neural net. On this side, I have input here. Maybe there's some pixels. We're doing our convolutions. I'm skipping a bunch of steps here, but here on the output side, we have some prediction for the class that exists in the image. So is this a cow, or is this a cat, or is it a car? And as a byproduct of that computation, we end up with these hidden representations in the middle. And the question we're trying to ask is, what do those hidden representations actually represent? And so this is something people have asked of neural nets a lot. And we're going to ask it in a slightly different way by comparing it to word embeddings. So remember, we just talked about word embeddings. In particular, we talked about skipgram. We have our one hot vector comes in, and we're trying to predict the nearby words. And again, we get this hidden representation in the middle as a byproduct of that prediction. So we have two kinds of hidden representations. So we have hidden representations that come out of a convolutional neural net. It's trained to predict what's in an image. And we have a hidden representation that comes out of skipgram. It's trained to predict nearby words. And so here, we're going to, each one of the classes I was going to say Instagram. One of the classes in ImageNet has a word associated with it, right? So like this is a cat. It actually has really specific cats, but you can imagine cat and car and cow. So we're going to use the word vectors for those class names in order to try to compare word vectors to the representations from convolutional neural nets. Does that make sense? So I have a picture of a cat. I'm going to run it through my convolutional neural net, get hidden representations. I'm going to say those are hidden representations for cats. And I'm going to take my word vector. I'm going to say, how similar do cats look to my word vector for cat, essentially. So what I'm asking is, do convolutional neural nets learn something like word vectors learn? So it's sort of like what we did before when I was saying, you in your brain, please compute for me how similar two words are. We're doing a similar thing now, except one of our spaces is built from the hidden representations of convolutional neural nets. So now every point in our space, instead of being computed from a word vector, now is computed from the hidden representation of a CNN. And we'll go layer by layer. So let's just say we're doing the first layer. We're going to take those hidden representations for particular words and plot them as points in space. And so now we have these two spaces. And we want to know how similar are these two representations. The axes have nothing to do with each other. All we're interested in is the distance between points. So not only do the axes have nothing to do with each other, the dimension of these spaces is different. So word embeddings are like hundreds of elements long, and then hidden representations can be thousands. Other questions? So we'll get into the meat of this, well, sort of. I'll at a very high level, talk about this. So essentially what we're going to do is take convolutional neural nets, and we'll run through an example of each one of the ImageNet classes, and that will give us one vector for each one of the classes. And then we'll take the words that correspond to those ImageNet classes, and we're going to take those word vectors. So we have two sets of hidden representations, and they have something to do with each other. So this is the hidden representation for the image of a cat, and this is the hidden representation for the word cat. So what we're going to do is calculate the pairwise similarity of all of these representations and the pairwise similarity of all these representations. We end up with two correlation matrices. And so essentially what we want to know is, are these correlation matrices related to each other? So I'm skipping a lot of details here because we don't have a ton of time. But we're essentially just asking, how similar are these two representational spaces? How similar are the distances between concepts in each space? So you can think of this as just essentially computing the correlation between the correlation matrices. We're doing something a little more complicated, but that's what you can sort of just put in your head for now. So on the x-axis here, this says 2 versus 2 accuracy, so just replace that in your head with correlation of correlation matrices. On the y-axis here. And on the x-axis here, we're moving through the complexity of the CNN. So the very first point here is actually the pixels. So we're going to calculate the correlation between the actual pixels of the image before the CNN even gets to it. And we actually see that the representation of, there's a small but non-significant correlation between just the pixels of the images. So the pixels of the image for cat and cow, or let's say cow and horse, are correlated, not significantly, but they're like, 60%, which is, I was surprised. But the reason is that like horses and cows, you see them outside, so like most of the pixels in the top are blue, most of the pixels in the bottom are green, something like that. So you can see how like very low level features of the images would actually give you some degree of correlation. And as we put it through these, so this is as we move through the convolutional neural net, this is VGG16. As we move through the CNN, we actually see that the correlation between the word and the CNN representations actually increases. So that means that the convolutional neural nets, as they're doing this task of computing new kinds of information from the previous layer, they're actually moving towards a representation that looks like word vectors. So that means they're learning something from images that looks something like word vectors. So we see this not just for VGG16, but this is ResNet50. So a similar pattern with some interesting bumps in accuracy, which if you're interested, you can look at the paper, especially in the supplementary material. There's a full graph of the architecture of the different neural nets. You can see where the accuracy goes up and down. And again, for another network, Inception V3. So these networks are learning representations that look like word vectors. And by look like, I just mean that they respect the distances between points in space. Yeah.
Don't you find this a bit strange? Because CNNs are supposed to look into visual similarities and not...
Yes, I found this very strange. In fact, I made my student do it, like check several times because So this is ImageNet. Yeah. So it seems strange until you think about it, right? Until you think about the properties of scenes, even in the first convolutional layer, will have some relationship to each other, right? So there's sky in the top and there's grass in the bottom if things are outside. So just that will get you some information, right? Things that are man-made have sharp edges. Things that are nature have soft edges. So you can think of the sorts of things that would get you some information, and then we start to, as you move up the hierarchy, you start to get more and more complex representations. And so if you actually look at some of the work that's looked at the sort of things that each neuron represents, you can actually see the complexity of the representations growing as you move through the neural net. So I was initially very skeptical of this, but I've been convinced that it's true. So essentially what we're saying is that models that learn to see learn something that looks like models that learn to read. Now, of course, they're both learning about the world, and so actually in some way it actually makes sense. They should learn something that is related to each other, right? They should learn something that has something to do with each other. We're also interested in how the layers behave during training. So hopefully you've seen graphs that look like this. So here I'm training my neural net. This is my epochs. This is my error. So my error on my actual training data goes down, and my error on my test data goes down to a certain point, and then it stops. So we're interested in the behavior of the layers during this process of training. So as this error is decreasing, what are the layers looking like? What do the layers look like? So I showed you the results on a pre-trained model. That's what it looks like at the end. And so the question is, how do the layers behave during this training process? So we can say that another way. Which layers learn first? And so we can rephrase that as, where do the 2 versus 2 accuracy rise first? And the 2 versus 2 accuracy, remember, you're just thinking a correlation between those two matrices. Does anybody have any guesses? So the answers are shallow layers and deep layers. So where do you think the representations will look more like word vectors first? Deep? So somebody should say shallow, because that's the other option. Shallow, very good, okay. So those are the two options, and this is the graph that tells us the answer. So here, these are the shallow layers, and these more pink and yellow are the deep layers. So the ones that learn first are actually the shallow layers. So they learn first, they create these representations, and then actually after that, they're quite stable. So the representations sort of snap to something that's useful, and then they stay the same. And then most of the learning actually happens in the deeper layers towards the end. So as we're doing that fine tuning, what we're actually doing is trying to get those deeper layers to fit the data better. And they're getting closer and closer to word vectors. And that kind of makes sense, right? You can't build a deep layer. In retrospect, it makes sense. You can't build a deep layer. You can't have it be close to word vectors until the thing before it is stable and sort of fixed. You've probably also heard of adversarial images. So I'll tell you quickly about them. So an adversarial image is when we take an image and we change it just a little bit, essentially add some special noise to it, and that makes the convolutional neural net misclassify it. And so there's some pretty striking examples of this. So in every example here, this is the true image, this is the noise they added, and this is the resulting image. And they were always trying to make the classifier predict ostrich. So here, bus still looks like a bus to you and me, but the CNN's very sure that it's an ostrich. So we can do this by choosing any target class. We could choose ostrich, we could choose anything we want, cat. And we can get the CNN, if we have access to the internal weights, we can get the CNN to predict this thing. And so what we would like to do now is ask, is the hidden representation for an adversarial image? So if we take this image of an ostrich and we run it through our CNN, what do the hidden representations look like? Do they look like an ostrich, or do they still look like a school bus? So we can't use this test. We're going to need a different test now, but it's actually built on the same idea. So essentially, we have one convolutional neural net representation. So we get that by taking the adversarial image and piping it through our CNN. We'll get a hidden representation for the adversarial image. And then we have the true word vector and the adversarial target. So here, this is school bus, and this is ostrich. And so now what we're going to do is take this hidden representation. We're going to essentially compute the correlation matrix row for the adversarial image by choosing a whole bunch of non-adversarial images and just computing the correlation between the hidden representations. And we'll do sort of the same thing for word vectors. We'll take those same non-adversarial image labels, the word vectors associated with those labels, and we'll calculate the correlation between the true and adversarial target word vectors. And so all of that is a little complex, but what you can essentially say is, does this adversarial image look more like the true or adversarial target? So essentially, is the convolutional neural net being fooled? So the answer is yes, because it's an adversarial example. At some point, the net is fooled by this example. But the question is sort of, what does that fooling look like as we move through the layers of the neural net? And so we're going to calculate essentially the correlation between the adversarial image and the true vector, and the adversarial image and the adversarial vector, and ask which one is closer. So we'll get high accuracy if most of the time the adversarial image is closer to the true vector. That is the question. So the question was, is it going to happen in the deep layers or the shallow layers? So start thinking about that, because I'm going to have a slide that says exactly that. So we have to choose the target classes. And so in order to do a fair comparison, we chose 6 target classes. We chose essentially the target class corresponding to the word that's closest to the true vector, as well as some in the middle, and also the one that's farthest from the word vector. So essentially, we're covering the semantic space by choosing very similar things, as well as very different things and everything in between. So what I'm going to show you is the average over all 6 of those target classes. And I'm asking you the question, do you think, we're going to say it's high if the, let's check. If the image-based vector is more like the true class, we'll say the 1 versus 2 accuracy is high. So in what layers do you think the adversarial image will be more like the true class? Deeper layers. Anybody? So now also someone should say shallow. Shallow, very good, thank you. So the answer is actually, in the shallow layers, the convolutional neural net is not fooled. It still knows that this image is the true class. But as we move through this convolutional neural net, it becomes fooled. the errors that we have, the small amount of white noise that's in the input image, essentially snowballs. So here the neural net is not fooled. It knows that this is still a school bus. But as we move through the neural net here, essentially we end up looking like an ostrich. So hidden representation moves towards something that looks like an ostrich just because of that white noise. And the white noise was formulated in a way exactly to fool that particular neural net. Mm-hmm. So the shallow layers are very low-level things in the image, so things like straight lines, gradients, and then as you move up through the convolutional nets, you'll get things like curved lines, and you'll get spirals as you move up, and essentially they get more and more complex as you move through the neural net. So there's some papers showing that exact fact that the complexity of the representations increases as you move through, starting from very simple straight edges, essentially, edge detectors in the first layer, to much more complex things in the later layers. Yeah?
Does this kind of behavior also happen for non-adversarial images, like such kind of drastic change in the two-value class?
So we saw the behavior on non-adversarial images, and we saw that essentially it was always, so you can think of it as more similar to the true class, and it became more similar, even more similar to the true class as we went through the neural network. Any other questions? Uh-huh.
Isn't this an artifact of how adversarial images are found?
Mm-hmm. Yep, so this is, our adversarial images, the kind that I used here, are formulated for the neural nets that we're testing them on. So if you do not have access to the weight vector that sits behind the neural network, you could not make these kinds of adversarial images. And so one of the questions is, if a network is more robust to adversarial images, would these tests pass? And also, could you use these sorts of tests to build a network that's less susceptible to adversarial examples? Totally open research questions. So this does actually not tell us anything about probability. It just tells us whether or not the hidden representations look more like the true or the adversarial class. But I think from that you could probably infer that it becomes more sure.
But for the adversarial ones, like we are somehow say, okay, it's for the true class, and then when we go deeper, it changes somehow, right?
Uh-huh.
So this change can help us to figure it out. This is an adversarial.
Exactly. So his question is essentially, can we use the fact that things look different as we're moving through the network for this adversarial image? It starts out looking like one thing and then it ends up looking like something very different. So could we use that fact to detect adversarial examples? And I think yes. I haven't actually done it yet, but it seems like a reasonable thing you might want to do. And if you do it, you should cite my paper. Dharma Retnam, this one's under review, but 2017. Okay, I'd love to see somebody do that. I think it's a great idea. If you want to work on it, I'm accepting graduate students. Okay. So we really just scratched the surface of NLP today. So NLP is a huge field. So here's a picture I was going to show you at the beginning, but I didn't want you to get overwhelmed. So this is a sentence, and the amount of things encoded in this sentence, the kinds of information go all the way from just character level things, like here's an A, to morphology. I talked about how words have different parts, talk and ed, as well as the words. So we talked about the word level today, but there's also syntax, so how words go together. And there's also semantics at a higher level. So we talked about word-based semantics, but we could also talk about what do sentences mean, and what do paragraphs mean, and what is this book about, and so on and so forth. As well as discourse, which has to do with sort of knowledge that we all have as we're having conversation. Knowledge that is integrated into conversation. So we really just scratched the surface, and you could take an entire class on this if you were interested, and I hope that you will. We talked about semantics and word embeddings, and then we talked about how skipgram is related to convolutional neural nets. And there's a ton more to talk about, so I'll just put up this slide with some resources to end, and I'll take any questions you have.